Let's look at a voltmeter. Voltmeter connected across a resistor. Connected across a resistor to measure the PD in a potential divider circuit. So, why is this of a point of interest, since we know that a voltmeter is a device that is used to determine the PD of a resistor? Why is it the point of discussion now that we are saying that you want to use a voltmeter to determine the PD across a resistor, when you can actually calculate the PD across the resistor? So you have to note that the measured voltmeter reading is not necessarily the same. Is not necessarily the same as the calculated PD across the resistor, except under certain conditions. So, for example, you have resistor R1 and R2 connected in a potential divider circuit to a power supply of EMF E. So we have explained to you before that if I want to calculate the PD across R1, it will just be R1 over R1 plus R2 times E. But if I connect the voltmeter across R1 to measure the PD across R1, the voltmeter reading across R1 will not necessarily be equal to the calculated PD across R1. The reason is that the measured value, more often than not, will be less than the calculated value of the PD across R1. Now note this: if a voltmeter is connected across a resistor, the voltmeter reading is equivalent to the PD of the combined resistance across the voltmeter. I repeat that. If a voltmeter is connected across a resistor in a circuit, the voltmeter reading is equivalent to the PD of the combined resistance across the voltmeter. Now in this case, it will appear as though the combined resistance across the voltmeter is R1. And we have said that the voltmeter reading is the PD of the combined resistance across the voltmeter. And in this case, it will appear as if the combined resistance across the voltmeter is R1. Therefore, the voltmeter reading should just be given as R1 over R1 plus R2 times E. However, this voltmeter also has its own internal resistance. Let us call it R substitute V. Therefore, the voltmeter reading is not the PD across R1, but the PD across the combined resistance across the voltmeter, which is basically the resistance R1 in parallel with the resistance of the what? Of the voltmeter. So we can say here that the voltmeter reading is the PD. The voltmeter reading is the PD of the what? Of the combined resistance. Of the combined resistance across the voltmeter. Across the voltmeter. Which in this case is R1 in parallel, which is R1 in parallel to what? RV. So the voltmeter reading is the PD across the combined resistance across the voltmeter, which is R1 in parallel to what? RV. So if R prime is the combined resistance across the voltmeter, which is equivalent to R1 in parallel to what? RV. Therefore, the voltmeter reading will be given as R prime over R prime plus what? R2 times what? Times E. That will be the voltmeter reading. Because in this case, we have now said that the combined resistance across the voltmeter is R prime. And prime is the combined resistance of these two resistors in parallel. So we can now assume that the combined resistance across the voltmeter is R prime. So R prime is representing everything here. R prime is representing everything here, which is basically R1 in parallel to what? RV. So I can then use the potential division equation that the voltmeter reading will therefore be what? R prime over R prime plus R2 times 1 times E. So I can therefore find R prime using the basic method of calculating the combined resistance of two resistors in parallel here. So I can say that 1 over R prime is equal to 1 over 1 RV plus 1 over 1 R1. So you take the SM of the two. R1 RV, R1 plus 1 RV is equal to 1 over 1 R prime. So that R prime becomes 1 R1 times RV over 1 R1 plus 1 RV. So after I've calculated R prime, I can then substitute into this equation to then determine the voltmeter reading across the voltmeter. So this voltmeter reading will be less than the theoretical value of the PD across R1, because when two resistors are connected in parallel, their combined resistance will be less than any of the two individual resistances. So the voltmeter reading now depends on R prime and not just on R1 or 1 RV. And since R prime will be less than any of these two resistors, the voltmeter reading will be less than the PD across what? R1. Is that okay? Now note this. Note, if the internal resistance of the voltmeter is infinity, so I can say that R sub V is equal to infinity. So the combined resistance across the voltmeter, which is 1 over R prime, is equal to 1 over RV, which is now infinity, plus 1 over 1 R1. So if I continue that to be 1 over R prime is equal to 1 over infinity is what? Is 0, plus 1 over 1 R1. Therefore 1 over R prime is equal to 1 over 1 R1. 1 over R1. Therefore R prime is equal to what? R1. Therefore the voltmeter reading now becomes what? R1 over R1 plus R2 times what? E. So note, if the voltmeter is having an infinite internal resistance, the voltmeter reading will therefore be the PD. It will be reduced to the PD across what? R1. In that case, that voltmeter is considered to be an ideal voltmeter because it is measuring the PD across what? R1 without its own internal resistance contributing to the combined resistance across R1. Because if I connect this voltmeter across R1, my intention is basically to determine the PD across R1 without necessarily considering the effect of the internal resistance of the voltmeter. If the voltmeter has its own finite resistance, the voltmeter reading in that case will not just be the PD across R1, but the PD of the combined resistance between R1 in parallel with what? R sub V, which in this case we are referring to as what? R prime. Okay, but if the voltmeter has an infinite internal resistance, the voltmeter reading will therefore be the PD across what? R1, because the internal resistance of the voltmeter in that case does not contribute to the combined resistance across the voltmeter. So note, this therefore means that, note, if internal resistance of the voltmeter, if internal resistance of voltmeter is infinity, the voltmeter is said to be an ideal voltmeter. Okay?